Introduction to Statistics in Lesson 1, while in Lesson 2 we will focus on measures of central tendency, and in the third and last lesson the focus is on measures of dispersion. In Lesson 1 we focus on an introduction to statistics. Outcomes for Lesson 1. In this lesson we will focus on important stages in statistics, quantitative and qualitative data, continuous and discrete data, convert categorical qualitative data into discrete quantitative data, and finally we will consider some ways to organize data. Important stages in statistics. Many important issues often confront the citizens of a country. When addressing these issues, appropriate data should be collected so that informed decisions could be made. Data collected should be organized and represented in such a way that it conveys a meaningful message. Data organized and represented in meaningful ways can then be analyzed to identify general trends and features. General trends and features in turn can be utilized to interpret data in order to draw conclusions and make predictions. Let us focus on quantitative and qualitative data. Now, data refers to pieces of information that have been observed and recorded from an experiment or a survey. Note, data is the plural for datum, and therefore one should say the data are. Now, quantitative data are data that can be written as numbers, and it can either be discrete or continuous. Now, discrete quantitative data can be represented by integers, whole numbers, and usually occur when we count things. Continuous quantitative data can be represented by real numbers. Qualitative data are data that cannot be written as numbers and can be classified into two groups, either as categorical or anecdotal. Now, categorical data can come from questions like your favorite color or pet, and it can sometimes be turned into quantitative data. Anecdotal data take the form of an interview or a story. Let us look at an example of discrete quantitative data. Now remember, discrete quantitative data are data that can be represented by integers, and it usually occur when we count things. Here is a good example. 20 learners were asked how many SMS messages they received the previous day, and the results are indicated here. Now, from this it is pretty clear that 3 learners received 6 SMSs, 2 7, 4 8, 1 9, 3 of them received 10, 2 of them 12, another 3 received 13, and 2 15. Now, one way to represent the data here are simply to construct what we call a dot plot. So this dot plot represents the number of SMS messages received by 20 learners. On the horizontal axis, we indicate the number of SMS messages, in other words the various categories, and on the vertical axis the number of learners receiving these number of SMSs. As I pointed out, 3 learners received 6 SMS messages. So we have 6 SMS messages. There's 1, 2, 3 dots opposite the counters 1, 2, 3 and 4. The same for 7. There will be 2 learners. 8, there's 4 learners. 9, only the 1 learner. 10, 3 learners. No learners received 11. So there's no dots here. 12, 2 learners. 13, 3 learners. And finally, 15 learners received 2 messages. Note, the data are illustrated by means of discrete dots or points. Now the word discrete means really that no dots can be inserted vertically. For instance, no learner can receive, not 1.5 learners can receive 6 messages, nor can dots be inserted horizontally, for instance, between 6 and 7. You cannot receive 6.5 SMS messages. So the position of the dots depends on an integer value. Right, like I said, you cannot put at 6.5 a dot, right, because it's got to be an integer. Furthermore, the dots cannot be connected by segments, so we cannot draw a graph connecting these points, as the in-between values will have no meaning. So this is what we really mean by a discrete type of data. Let us look at an example of continuous quantitative data. Now remember, continuous quantitative data are data that can be represented by any real number. A real number, as you will recall, is a number on the number line. Here is an example of such data. The heights of 10 learners are measured in centimeters, and we obtained the following results. Now, if we illustrate this graphically, on the horizontal axis I'll have the learner identity. On the vertical axis, the height of the learners. Please remember, any good graph should have a heading, and I think the heading here, heights of learners in centimeters, will be suitable. So what can we then do? We can then take the available data and illustrate it by certain dots or points, right, in this particular two-dimensional plane. Then I could use available methods and draw the best fit line. Now this makes sense in this case, because more dots can be inserted. Like you can see, I've inserted these 2 red dots here, which was not part of the available data. That's learner K and L. That's got different heights. You see, the height of the learner can be any real number. So therefore, values on this line in between the observed data make sense. So because the height of the learner can be any real number, we call this data continuous data. So all the numbers on this best fit line will make sense, and therefore you can see, depending on the type of data, you can classify it either as discrete or, as in this case, as continuous quantitative data. We now focus on categorical qualitative data and how we can convert it into discrete quantitative data. For example, in a class with 28 learners, they were asked what their favorite color is, and the responses were recorded in this particular table. So can you see there's 4 rows and 7 columns, so we have 28 responses. Now this is clearly categorical qualitative data, since each of the responses come from one of a small number of possible colors. We can represent exactly the same data in a different way simply by counting how many times each color appears, and then we obtained this particular table. Now we have changed the data, and this data is now discrete quantitative data, since each count of a color is represented by an integer. Let us look at a definition of some basic terms. We often speak about a population, which is a collection of all potential observations that can be found in a given situation. Like if you conduct a survey in a particular school, then you must ask this question to all the learners in the school, which is often not possible because for some reason some of them will not be there on a daily basis. For that reason, we rather focus on a sample. Now, a sample is a collection of observations representing only a portion of the population. Like in the school population, you may only ask the question to learners from a particular class, maybe the grade 10s. And then we often ask a question linked to a variable, number of SMSs. That we can indicate by a variable x. We are talking about single variable data that will have a value xi for a datum item or observation number I. So if there is, for instance, 10 learners that we ask a particular question about, then the datum items can be represented by x1, x2, x3 up to x10. Let us focus on the arrangement of data. Now, ungrouped data or raw data is a collection of observations that has not been arranged in any meaningful fashion. However, group data is an arrangement whereby raw data have been grouped into a series of equally spaced classes. The number of observations falling in each class interval is called the class frequency, and the resulting table that we will design is known as the frequency distribution table. Let us look at a method how to organize ungrouped or raw data. Now, if we look at ungrouped data or raw data that's not arranged, means data not arranged in any meaningful fashion, like in the example, the number of SMSs received, that's the variable x, on a certain day by 12 students, may be recorded in this way. So in other words, x1 is 0, x2 is 3, x3 is 6, and finally x12 will be 7. Now this can be further analyzed either by hand or by a personal computer, where you can use a program like Excel, typing it in and then sorting it. If we do that, this set of raw data can then be arranged either in ascending or descending order. So if, for instance, I organize this in descending order, I arrange it from the biggest value to the smallest. Or you can arrange it in ascending order, and this is from small to big. We now look at a method how to organize raw data as group data. Going back to the example of the 12 learners, where we asked the questions how many SMS messages they received. We want to group this as, or organize this as group data into 3 classes. Just something about a decision that we often need to make about how many classes we need to have. Now, one method, and please, there is more than one available method. I challenge you to go to Google and find out different ways in which you can decide how many classes there must be. Now, one easy way is simply to take the square root of the sample size. In other words, the square root of 12, that's approximately 3 point something, and for that reason we can organize this raw data as group data in which we have 3 classes. So now you've got to decide where must a particular class start and where must it end. Now the biggest value here is 8. Now 8 is not exactly divisible by 3, so therefore we rather focus on 9. So we therefore start with 0 to less than 3, so we include 0 but we exclude 3. Note that the class width is 3 here, because 9 divided by 3 gives us 3. So the next class will start at 3 and it will go up to all values less than 6. And the last class from 6 to less than 9. And all we do then is simply count. Right. I've already arranged these in a particular order. Can you see it's not unarranged? We have done it in the previous one. So if I start tallying, how many observations will fall in the first class? Now that is clearly 0 and 2. So the frequency is 2. By the way, this is my frequency distribution table. So then we go to our next class. So there you have 2 3s, a 4, 5, and another 5. That makes a group of 5, and 2 more 5s. So the frequency of this is 7. You should be familiar with this, where we make bundles of 5. Right, so 4 observations, and the 5th one then complete the bundle. It just makes it easy to count at the end. We don't have to count each one physically. And then finally, in the 3rd class, there clearly we have only the observations 6, 7, and 8, and the frequency of that is equal to 3. Note the sum of the frequencies of the 3 classes. So you have f. This notation means the sum of I from 1 to 3, so I can be 1, 2, or 3. If I is 1, we have F1, and F1 is 2. If I is 2, we have F2. So in other words, the frequency of the 2nd class is 7, and F3 is equal to 3. So this is the sum of all the frequencies of the classes. So if I expand this will really mean it's F1 plus F2 plus F3. And that clearly is 12. And this is the size of the sample size. So in this particular column here, we describe the intervals. So to each interval you must attach a limit. The limits describe the interval of each class. There is a lower limit and an upper limit. For instance, the lower limit of class 2 is 3, while the upper limit of class 3 is 9. Another useful notation is to use the square round bracket notation. Now in this particular case we include the first number, 0s, 3 and 6, so we include the lower limits, but we exclude the upper limits, so we will make use of this first type of notation. But sometimes you will have a situation like, for instance, this may end on 9. It may include 9 but exclude 0. Then the second notation will be more suitable, where the lower limit is excluded while the upper limit is included. So in this case L is the lower limit and M the upper limit. Just by way of repetition, that we use the symbol N, which is the sum of the frequencies of all the classes. In this case it's 12, is what is known as the sample size. Let us more specifically look at equivalent interval notations. In the previous example we had the description for the range of messages M. Right, and this was type of a verbal description. And we've identified the frequencies for the various classes. We could use this type of notation where we indicate the variable M, and we say M is smaller than 3 but greater or equal to 0, or M is less than 6 but greater or equal to 3, or M is greater or equal to 6 but less than 9. Now this implies the word but or and in between. A much better way, of course, is simply to use the interval notation for M, where we say it ranges from 0 to 3, the first class, and the square bracket means the 0 is included, 3 is included, and the 6 is included. So the lower limits are included, but the upper limits are excluded. You see, here to say that you must say less than to exclude the upper limit. Here we just simply remove the equality to show that the upper limit is excluded. Here the round bracket indicates that the upper limit is excluded, but the lower limit included. Here the lower limit included is indicated by the equality. So in all three these cases, the class width is equal to 3. In other words, the upper limit minus the lower limit. The upper limits are 3, 6 and 9 in all three cases, while the lower limits are 0, 3 or 6 in all three cases. Next we focus on how to organize ungrouped or raw data by means of a stem and leaf plot. Now a stem and leaf plot is useful for organizing relatively small sets of data. It is a quick and easy way to order the display in a set of data. To do this, the leading digits forms the stem, while the trailing digits becomes the leaf. So let us look at this example where we want to transform the data into a stem and leaf plot. So here we have the data. Now if you look at this carefully, the tens digit here will be the stem, while the units digit will be the leaf. So where we have a single digit, we will actually imagine a 0 in front of the 3, the 1, the 7 and the 2. So we write down firstly our stems, and the stems, in other words the tens digit, can either be a 0, a 1, a 2 or a 3. So we have 4 stems, and then we just simply start from the left. So The 3 will be a leaf belonging to the stem 0. The 7 will belong to the stem 1. The 1 to the stem 0. The 9 right, to the stem 2. The 7 to the stem 0. The 5 to the stem 3. The 10, or this particular 0, to the stem 1. The 7 to the stem 3. The 2 to the stem 0. And the 25, in other words, just focusing on the 5, to the stem 4. Now, this is an unordered stem and leaf plot. But once you have this, it's relatively easy just to arrange the leaves in a proper order to obtain this. And this is then commonly known as an ordered stem and leaf plot. We're now in a position to tackle tutorial 1, which deals with statistics basics. Suppose that 35 students obtain the following marks out of 50 in a mathematics or for a mathematics tests. And here is the marks, not arranged in any particular order. The first question is that you need to use a stem and leaf plot to arrange the raw data in ascending order. And then group the raw data in a frequency table of 5 classes. Why the 5 classes? Again, if I assume that the method that we use to find the number of classes depends on the square root of the sample size. Now the square root of 35 is nearly 6, but not, so therefore we use 5 classes. I suggest that you pause the video, do tutorial 1, and then come back and view possible solutions. Let us consider a suggested solution to problem 1 from tutorial 1. You need to use a stem and leaf plot to arrange the raw data in ascending order. So here's the raw data. So firstly, I construct a stem and leaf plot. Note that this stem and leaf plot is actually an ordered one. So there's actually an in-between phase which I leave for you. You will firstly identify the stems again as the tens digit. So it ranges from 0 to 5. So there's actually 6 stems, and then take or record the leaves. So what you should actually do is before this have an unordered stem and leaf plot. So you will start off by recording the 6 as the first observation with the stem 4 and so on. And then just rearrange it. So I left out one stage here, and I leave that for you as an exercise. Once we've got this, it is easy to arrange this table containing the data, but now in an ascending form. Alright, so your first observation is 8, then 10, 12, 15, and so on. So that should be relatively easy to complete. Let us look at a suggested solution to problem 2 from tutorial 1. You need to group the raw data in a frequency table of 5 classes. So if I make use of the ordered data which we obtained from the previous activity, then I can, just to make it a little bit easier, instead of having 5 rows, I could arrange it in that same order but now in 2 rows. And then I can easily construct the frequency distribution table. So we'll have 5 classes, and note, because the maximum is up to 50, we will select the class width to be 10. 0 is not included, so here we use the interval notation, but we include the upper limits. And then it's simply a case of to tally the number of observations in each class. So in the first class you can clearly see we only have the 2 observations, so the frequency of class 1 is 2. In a very similar way, we count the number of observations in class 2, and that we see is a bundle and 1. In other words, the frequency of the second class is 6. Counting the number of observations in the third class, and we see that's 14, and then count the number of observations in class 4, which we see is equal to 8, and finally counting the number of observations in the last, or class 5, we get 5. Of course, the sum of the frequencies must be equal to the sample size, which in this case is 35. In lesson 2, the focus is on measures of central tendency. The outcomes for lesson 2. In this lesson, we will focus on the display of group data, the calculation of the mean for ungrouped data, estimation of the mean for group data, the calculation of the median and mode for ungrouped data, and identification of the median and modal classes for group data. Let us look at the display of group data. Group data can be displayed by means of an histogram, and to construct a histogram we construct a column on each class interval. The vertical height of the column match the frequency of the class, and we can also display it by means of a frequency polygon by plotting a dot above the midpoint of each interval. This particular location is the value of the class mark. The dots are connected by straight lines and anchored on the horizontal axis on the left and the right. A histogram and a frequency polygon can both be displayed on the same graph. Let us look at an example of an histogram in which we display group data. Assume we have this frequency distribution table in which we have 5 classes. The interval indicates masses, and the frequency for each particular class are also indicated. Now, to construct a histogram, we firstly place on the horizontal axis the mass of the objects, and on the vertical axis the frequency. So we must make provision for frequency up to at least 22. So then we construct a column on each class interval. So in other words, we have a column starting at 10, ending at 15, one starting at 15, ending at 20, and so on. So we must have 5 columns. The height of, or the vertical height of the column is matched by the frequency. So the first column, the height must be 8. So we stop at the frequency of 8. For the second column, the height must be 13. The third one, 22, and so forth. Important that we label the histogram properly. So there's a label on the horizontal axis. It means here we indicate the mass in milligram. There's a label attached to the vertical axis. Here we have the frequency, and we need to have a suitable heading. In this case, the mass of the objects will do. Let us look at an example of a frequency polygon and a histogram on the same grid. Let's look at the same frequency table where we've added an additional column in which we indicate the class mark xi, which is simply the midpoints for each of the intervals. In addition, we've added a class in the beginning and a class at the end with a frequency of 0, and this we simply do because we would like to anchor the frequency polygon. So if we can go back to the situation where we've sketched a histogram, Then we plot a dot above the midpoint of each interval. So what we really do here is we plot the class mark against the frequency of the class. Now it's important too that we connect these dots with straight lines, and to complete the frequency polygon it needs to be anchored at the midpoint of the previous class and the midpoint of an additional class at the end, to which of course we allocated frequencies of 0. So we're not going to contaminate data by doing this, by adding 2 additional classes with each with a frequency of 0. So this is simply to ensure that the polygon is anchored. And then to finish it off, we need to label it properly. We've labeled the horizontal axis, we labeled the vertical axis, and we need to write down a suitable heading. A frequency polygon can be displayed on its own for group data. So again, if I have this group data, I simply plot the class mark on the horizontal axis against the frequency on the vertical axis, and then we add the 2 additional classes to ensure that we anchor the polygon. So if we just plot midpoint or class mark, midpoint of an interval is the same as the class mark against frequency, this is what we will get. But then we need to anchor the frequency polygon on the left, and we need to anchor it on the right. Of course, you need to have the label, the frequency, class mark MI, and a suitable heading, and then it needs to be anchored. And to do that, of course, we've added the 2 additional classes. So we anchor it at 37.5 and at 7.5. We're now in a position to tackle tutorial 2, where the focus is on a histogram and a frequency polygon construction for group data. If we go back to our example, where we have the test marks obtained by 35 students for a mathematics test out of 35, and we have this frequency distribution table. All I did here is add an additional class in which we have the class mark or the midpoint of each interval indicated. So it's expected of you to construct a histogram for the data as well as a frequency polygon for the data. I suggest that you pause the video, do tutorial 2, and then come back and view possible solutions. Let us look at the suggested solution to problem 1 of tutorial 2. You need to construct a histogram for the given data. So what we do here is we construct 5 columns, where the column width or the column width here will match the class interval, and the height of the column must match the frequency. So we construct columns, the one starting at 0, ending at 10, the next one from 10 to 20, from 20 to 30, 30 to 40, 40 to 50, and the height of each column depends on the frequency. So the first column is 2 units high, the second column 6 units high, the third one 14 units high, next one 8 units high, and the last column 5 units high. Then we need to label it properly. Now on the horizontal axis we have test mark intervals, while on the vertical axis we have the frequencies for each class, and then we must have a proper label at the top, namely test scores of 35 students should be a suitable heading. Let us look at a suggested solution to problem 2 from tutorial 2, in which you need to construct a frequency polygon. So what we're going to do here on the horizontal axis, we're going to place the class mark. On the vertical axis, we place the frequency, and we add two additional classes, one also with a class width of 10, ranging from -10 to 0, with a midpoint of -5, and of course with a frequency of 0, and this is simply to ensure that the frequency polygon can be anchored on the left. And we also add an additional class at the end with ranging from 50 to 60, with a midpoint or a class mark of 55, and to that we also allocate a frequency of 0 so that we can anchor the polygon on the right. Now once we have all these info, we simply plot the class mark against frequency. So we start here at -5 and the frequency is 0. The next one, the class mark is 5 and the frequency 2, and so on. And once you have plotted all these points and connected them with straight lines, this will be the frequency polygon. All that is left now is to label it properly. On the horizontal axis we have the class mark xi, on the vertical axis the frequency fi, and a suitable heading will be the test scores of 35 students. Next we focus on measures of central tendency. We will consider the following three measures of central tendency. Firstly, the mean or the average of the observations, the median, the middle value of the observations, and the mode, which is the most frequently occurring observation. Let us focus on how to calculate the mean, and the mean is indicated by the symbol x bar. To calculate the mean, we simply add the observed values, xi, and divide the sum by the number of observations. This is when we have ungrouped data. Then the mean is the sum of the observations divided by the number of observations. If we have group data, then we determine the product between the class mark and the frequency of the class, and we find the sum of all these products and divide it by the number of observations or the size of the sample. Let us look at an example where we calculate the mean of ungrouped data. So assume we have these 6 observations and we want to find the mean. And because it's ungrouped data, the formula that we use is that the mean is the sum of the observations divided by the sample size. So we simply add all the observations and divide it by 6. And this sum is 93 divided by 6. It's 15.5 or 15,5. You can use a calculator either as a calculation or a checking device. In order to use your calculator, you will simply input the data into your calculator by using a single variable stats mode, and then you can recall the mean for the data. Let us look again at this example, but now specifically focus on how we can use the calculator either as a calculation or a checking device. In order to use your calculator to determine the mean, we go to mode, statistical mode, and select single variable data. All we do now is input the data values, namely 7, 13, 15, 17, 20, and 21. And now after you've input the last one, you can clear the screen. Now we use the stats variable value box, this one here, which is a second function. and we can then recall what we want. Now if you go to option number 4, there we see two things that's applicable at this stage, namely the sample size and the mean. So if I select option 2, it then shows me that the mean is equal to 15,5 as we obtained through the manual method. Another option is to use this formula. So if I go here again and go to option number 3, which is the sum, selecting number 2. Now this sum, if you enter it, it will show you that the sum is 93. But I want to do a direct calculation. So I can go here again, fetch the sum, option 2, and then divide it by n. So if I go into my variable box here, and option number 4, selecting number 1, then you see on the screen we have sum x divided by n. If I enter that, I get 15.5. Just one more action. I could use the stats variable box to check the sample size, which is option number 1, and that clearly is equal to 6. So you can either do this before or after you've completed this problem. If I do it afterwards, I use the calculator as a checking device. If I use it before the time, then of course I use my calculator as a calculating device. Let us focus on the calculation of the median for ungrouped data. The median, which is normally indicated by M subscript E, is the middle value. This is also, you'll see later on, known as percentile 50. In other words, 50% of the data values will lie to the left or will be less than, and 50% will be to the right or greater than the middle value. The location or the rank of the median is always in position n plus 1 divided by 2. Provided that, of course, we have arranged the data in a meaningful way, either ascending or descending order. So if you have an odd number of data values, like in this case we have 5 data values, then the location of the median or the rank of the median, according to this formula, is 5 plus 1 divided by 2, that's 6 divided by 2. So in other words, it will be in the third position. And if we check this, the number 14 or the data value 14 is in the third position, therefore the median is 14. Note that 2 data values lie to the right and 2 lie to the left. So in other words, 50% to the right and 50% to the left. What in the case if the number of observations are even? If it's even, like in this case, then we have in total we have 6 observations. So firstly we need to find the location of the median or the rank. So the position or the rank is 6 plus 1 divided by 2, so it's in position 3.5. Or that simply means it will lie midway between the third and the fourth one. So somewhere midway between 14 and 17. And therefore to calculate it, we add 14 and 17 and divide by 2, and therefore the median is 15.5. So the median is then somewhere in the middle between these two. And note again, then 3 data observations will be bigger than that, while 3 data value observations will be smaller than that, or 50% will be greater than that, or 50% will be smaller than that. Let us focus on how to calculate the mode for ungrouped data. The mode is the most frequently occurring observation. For ungrouped data, the mode, which is normally indicated by M subscript O, can be found by inspection of the observations. Consider the ordered ungrouped data. Then it is pretty clear that the observation or the data value 12 occurs twice, right? So therefore the mode for this set of data values is equal to 12. There can sometimes be more than one mode. Looking at this, you will see that the observation 6 have a frequency of 3, and the observation 9 also have a frequency of 3. So therefore 6 as well as 9 can be a mode for this data. So this data is then bimodal, as both 6 and 9 are modes for this data set. Think in terms of if you want to make a dot plot, then of course you will get peaks in the dot plot when the observation is 6 or 9. We can determine the skewness of data by considering the values for mean, median, and mode. So the relative values for mean, median, and mode is an indication of the shape of the distribution. If we put here the data observations and there the frequency of each one, and we get this type of shape which is symmetrical, then in such a case we find that the mean, median, and mode is actually the same value. It's the same central value. While the second possibility is where we have a tail which develops towards the right. This one is positively skewed because the tail developed towards the positive x direction. It is clear that where we have this peak is the mode, so therefore the highest peak indicates the x value that appears the most, right, the biggest frequency. The mean will be somewhere there, and of course the median must always be in the middle. So that will be the sequence. So in this particular case there is a few very large numbers. So here you will have your large numbers, and it's only a few of it. Another way of saying it is there's quite a few, or a very large number of small values. So a tail developed to the right. The mean and the median is dragged towards the right, and this is the sequence. The median obviously is the middle value. The median in this case is less than the mean, but the mode is less than the median, or the median is greater than the mode. It depends in which direction you want to read this. So this is positively skewed. In a similar way, if we have this type of shape, we call this negatively skewed because a tail develops towards the left or the negative side. So there where you have your peak, that's the highest frequency, that's clearly the mode. The median will be somewhere there, and the mean there. I should actually indicate the mean first and then show that the median must lie in the middle. So what happens here? We have more very large numbers or very few small number values. So a tail developed to the left. So the mean and the median is dragged towards the left, and this will be the sequence. So the median is smaller than the mode but greater than the mean. So by just taking these three central values or the values for central tendencies into account, we can sort of predict this type of distribution that you will obtain. We're now in a position to tackle a tutorial on measures of central tendency for ungrouped data, and this we will do in tutorial 3. So you are given a set of ordered ungrouped data. This is being arranged in ascending order, so it's ordered ungrouped data. Firstly, you need to determine the mode, median, and mean for the data set. And secondly, determine the skewness of the data, and you need to give a reason for your answer. I suggest that you pause the video, do tutorial 3, and then come back and view possible solutions. Let us look at the suggested solution to problem 1 for tutorial 3. You need to determine the mode, median, and mean for the data set here. So clearly the observation 14 appears the most, and therefore the mode is 14, while the value 13 is the middle value. Remember, you can work out the rank. If you count this, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 observations. So therefore there will be 5 to the right and 5 to the left. Or you could say 11 plus 1 divided by 2 is 6. So therefore the rank for the median, which of course is percentile 50, must be 6. So the data value in possession 6, right, is therefore the median. To determine the mean, we simply need to find the sum of the observations. Note that the observation 3 appears twice, so instead of saying 3 plus 3, you can say 2 times 3. The frequency of the 3, in other words, is 2, and in a similar way, the observation 14 will have a frequency of 3, so you can type it in like this. And then you can use your calculator to show that the mean is 10.64. You can use your calculator as a checking device, and this is exactly what I would like to show to finish off this particular slide. Okay, before we start with this, I want to use the fact that some of the data values appear more than once. For that, I need to switch on the frequency column. So I put the shift setup, and going down, there is the stats option number 3, and we switch the frequency column on. If I now select mode and the stats mode and single variable, then you find in comparison what we've done before, we now have a frequency column. So the observation 3 is there, so I only input all the different ones. Note it allocates a frequency of 1 to that. We have the observation 6, the observation 9, and the observation 10, the observation 13, the observation 14, as well as the observations 15 and 16. Now all of these have a frequency of 1, with the exception of 3 and 14. So if I press my down arrow, it will go to the top and go across, and we change that frequency of 3 to 2, enter that, and then alter the frequency of 14. I can just go down to that one, make that 3. Okay. What I can do now is go to my stats variable value box again. I can determine a couple of things. I can find a sum, and we should be able to confirm that that is 117. You can do a calculation, as I've done before, by selecting again the sum and then divide it by n, which we find in the variable box there, option number 1. So calculating this then gives us 10.636. So this is an approximate value. Of course, you could also recall this straight away by going to the variable box 4 and selecting option 2, which then show that the mean is 10.64, approximately correct to 2 decimal places. Let us look at a suggested solution to problem 2 from tutorial 3. We need to determine the skewness of the data. Now we've calculated the mean to be 10.64, the median to be 13, and the mode to be 14. So I've just placed them in the proper sequence from small to big. So therefore we can observe that the median is less than the mode, but the median is greater than the mean. So there's more very large values. The mean and the median is dragged to the left, so therefore the data will be negatively skewed. A tail will therefore develop towards the left. We want to estimate the mean of group data. So to calculate the mean for group data in a table, as we have here, we need to complete an additional column. We need to determine the product of the class mark and the frequency of each class, and then find the sum of these products, because this we know is the formula that can be utilized to calculate the mean for group data. So I simply determine the product between 17.5 and 6, 22.5 and 13, 27.5 and 20, 32.5 and 25, 37.5 and 12, 42.5 and 4, and then get the sum to be 2,380. And then we divide this 2,380 by 80 to get an answer of 29.75. Now we can use the calculator as a checking device to check the correctness of this particular answer, and this is exactly what I will do now. Before we do this, as before, we switch on the frequency column, and then we select statistical mode and single variables, and we type in all the class marks: 17.5, 22.5, 27.5, 32.5, 37.5, and 42.5. Of course, the calculator allocates a frequency of 1 by default to each. So we go down and across and input the correct frequencies, namely 6 for the first class, 13 for the second class, 20 for the third class, 25 for class 4, 12 for class 5, and 4 for class 6. Once you've input this, we can then recall everything. So let's just check, see if we've put everything in correctly. I'm first going to find the sample size. So if I go in my stats variable box under variables and recall n, and we find then that the value of n is 80. I can find the sum xi fi as well, and then we will check to see whether it's 2380. So I go into the sum option here. Now here you don't see a sum xi fi, right? But we simply select option 2, and we get 2380. You can straight away recall the value for the mean and check whether it's 29.75, going into the variable box, option number 2, checking that, we see that it's 29.75. We now focus on the location of the median class for group data. Now in the grade 10 curriculum, you only need to determine the location of the median class. There is actually ways that we can find the actual median as well for group data. In order to achieve this, if we go back to the example where we have the class marks for 80 learners, then we complete what we call a cumulative frequency column. So all we do is we accumulate the frequencies. So to the 6 I add 13 to get a cumulative frequency of 19. Then to that 19, if we add 20, we get 39. To the 39 we add 25 to get 64. To the 64, 12 to get 76. And finally add the 4. And then the cumulative frequency of the last class must be the same as the frequency, as the size of the sample. Now, the median is percentile 50. What does that mean? That means 50% of the observations must be less than the median and 50% must be greater than the median. Now, 50% of 80 is 40. Now, if you go to class 3, you can see in class 3 I've accumulated to 39 observations. Therefore, the median class is only the next class. So 50% or half of the values from the data set are less than the median. The other half must be greater than the median. So therefore, the median class cannot be the class 3, but the median is somewhere in class 4. I would suggest that the median is pretty close to the upper limit of class 3. It will be slightly bigger than 30, because 39 was pretty close to 40. But that is not our objective in grade 10. You only need to determine in which class do you predict the median will be located. So in other words, it will not be in class 3, but only in class 4. How do we determine the location of the model class for group data is the next question we look at. Note the mode is the value that appears the most, and it will simply depend on the class with the highest frequency. So the mode is that score which appears the most, and it will be located in the class with the highest frequency. So therefore there is no doubt that the modal class will be class 4, because class 4 has got the highest frequency. We're now in a position to tackle tutorial 4, dealing with the measures of central tendency for group data. So the test marks obtained by 35 students, again for a mathematics test out of 50, are summarized in the table below. We have had this, or we've looked at this table before. You need to determine the mean, the average, estimate the mean for this particular data, as well as the location of the median and the mode. So you need to determine the median class and the modal class. I suggest that you pause the video, do tutorial 4, and then come back and view possible solutions. Let us focus on a suggested solution to problem 1 of tutorial 4. You are given this particular table, and it was expected of you to determine the mean or estimate the mean for this group data. So we add the extra column here in which we calculate the product of the class mark and the frequency of the class. So 5 times 2, 15 times 6, 25 times 14, 35 times 8, and 45 times 5. Complete this and then determine the sum. So the mean is then the sum of all these products divided by the sample size. So it's 935 divided by 955, divided by 35, or 27.29. Again, I'm not going to do it. You can use your calculator as a checking device. In problem 2 of tutorial 4, we have a suggested solution for the questions here. You need to, in this case, determine the location of the median and the mode. As before, I add a cumulative frequency column here, and the median we know is percentile 50, so in other words 50% of the data observations must be less and 50% must be more. Now 50% or half of this is about 17.5. Of course that's not possible for learners, but we can clearly see that that magical number must be somewhere in this class. Right, so therefore clearly the median is located in class 3. The 14 is the highest frequency of all the classes, so therefore class 3 is also the modal class, and therefore the mode will be located somewhere in class 3. Like I've mentioned before, there's methods that can be utilized to estimate the median and the mode for group data, but we will not discuss it in the grade 10 curriculum. In lesson 3, we discuss measures of dispersion. The outcomes for lesson 3. In this lesson, we will focus on outliers, range of a data set, percentiles, quartiles, interquartile and semi-interquartile ranges, 5-number summary and box plot, and finally on the identification of percentile classes for group data. Let us look at outliers and the effect of outliers on the mean and the median. Now an outlier is a value in the data set that is not typical of the rest of the set. It is usually a value that is much greater or much less than all other values. Consider the example where we are given the heights of 10 learners in centimeters, and this has been ordered in ascending order. The question is, how will the data be affected if an exceptionally tall learner, say with a height of 181 centimeters, is added to the data set? Now if we calculate the mean and the median, now to calculate the mean, it's simply the average. So you take your calculator, you add the 10 data values and divide it by 10, then you find that the mean is 155,9. While to get the median, we must first find a rank, so it's 10 plus 1 divided by 2, so it's in position 5.5, 1, 2, 3, 4, 5, so midway between 156 and 157, therefore 156.5. If we add the 181 on the right hand side here, and then recalculate the mean, so in other words just add it to the previous sum but now divide by 11, you find that the mean is 158.18, and that the change in the mean, in other words, if you subtract the mean before the addition from the mean after the addition, you find that that change is 2.28. Well, if we look at the median, now we will have 11 values, and 11 plus 1 divided by 2 is 6, so the rank is 6. So therefore, it is the data value in position 6 is 157. So the change is only 0.5. So we observe, therefore, that the median is less affected by an outlier than the mean. Let us look at measures of variability of data. Now the measures of centrality, namely the mean, median and mode, each expresses the center of the observed data in a different way. So they are measures of central tendency. What is the tendency towards the center of the observed data? Should the need arise to express the degree to which individual observations differ from each other, other measures of variability are needed. The greater the variability between data values or observations, the more they will be spread out. So we are interested in the spread. How widely is it spread out? How compressed is the data? That is the major question. An example of variability of data are the following. Samples A and B below indicate the volumes of 500 milliliter milk cartons measured in a quality control laboratory by a quality controller. You find that if we went to factory A, that he selected 4 milk cartons, and this was the actual volumes in the 500 milliliter milk cartons. While in factory B, this was his findings. Now the variability of data sample B is simply the maximum observed volume minus the minimum observed volume, and that difference is 62 milliliters, while in sample B the variability is the maximum 511 minus the minimum 485.26. So if the quality control laboratory should recommend a supplier to a shop, then producer A should be preferred to be the preferred provider to a purchaser or a shop owner, because the variability is less. The range of data is a measure of variability. The sample range for ungrouped data is calculated by subtracting the smallest data value from the largest data value, like we've done in the previous milk carton example. However, the sample range for group data is found by subtracting the lowest limit of the first class from the upper limit of the last class, if the grouping was done in ascending manner. We now focus on percentiles. The definition of a percentile. The pth percentile is a particular value V that divides the data set into two parts, such that p% of the values in the data set are less than V, and 100 minus p% of the values are greater than V. Percentiles will always lie in the range from 0 to 100%. We will still look at various examples so that you'll understand this definition. To understand percentiles properly, we need to distinguish between three different aspects of a datum, namely its value, its rank, and its percentile. The value of a datum is what we measured and record during an experiment or a survey. The rank of a data is its position in the sorted data set. The percentile at which a particular datum is tell us what percentage of the values in the full data set are less than this datum. Let us look at the relationship between value, rank, and percentile of a data set. Consider this particular set of data consisting out of 6 observations. We can easily write down the observations, the value of each. We can rank each because it's arranged. The question is, why are the percentiles as indicated? For example, we say that value 13 is percentile 40 since there are 2 of the remaining 5. Can you see, if you eliminate 13, there's 3 above and 2 below. Now 2 out of 5 is 40% of the 5 values are less than 30, and that's why it's called percentile 40. Obviously 3 or 60% of the 5 values will be greater. In other words, 100 minus p, or 100 minus 40, or 60% will be greater then. How do we find the rank? Now, the general formula for finding the rank of the pth percentile in an ordered set with n values can be expressed in this way. R of p, the rank of percentile p, is the value of the percentile multiplied by a number that is 1 less than the sample size divided by 100 plus 1. Now this formula is not unique because some people say that we can calculate the rank simply by taking the percentile, multiply it by 1 more than the sample size and divide by 100. So we will actually use both of these in different situations. Let us test it according to our given data. For instance, percentile 40. If I want to know what is the rank of percentile 40, so I know that percentile is 40, so I replace p by 40. We know that the sample size is 6, there's 6 observations, minus 1 over 100, 6 minus 1 is 5, and if we simplify this, we get an answer of 3. Therefore, the rank of percentile 40 is 3, and therefore percentile 40 is 13. I challenge you to work out a couple of more ranks, and in the same way, if you know the values in the rank, see if you can predict the percentiles as we've done here for percentile 40. Sometimes the rank is not an integer. This means that the percentile lies between 2 values in the data set. The convention is normally to take the value halfway between the 2 values indicated by the rank. But again, this is not a universal principle. We're now going to use the rank formula to calculate percentiles. So you are given this data set consisting out of 9 observations, and we need to determine percentiles 0, 25, 50, 75 and 100. So firstly we sort the data values and then allocate a rank from 1 to 9 to each of them. This is the rank formula that I will utilize. So we then calculate the rank of 0%. So P is 0. N minus 1, 9 minus 1 is 8. So obviously this is 0 plus 1. So the rank is 1. So percentile 0 is 7, which is the minimum value. That implies, remember, according to the definition of a percentile, it means that 0% of the observations will be less than 7. Once you eliminate the specific percentile, namely 7, there's of course no values below 7, and that's 0%, while 8 out of the remaining 8, or 100%, will lie above. Percentile, if we focus on percentile 25, the rank of that is 25 times 8 divided by 100. Now 25 goes in 100 4 times, and 8 divided by 4 is 2, plus 1 gives me 3. So the rank of percentile 25 is 3, therefore 14 will be equal to percentile 25. This is also known as quartile 1, the lower quartile, or simply Q1. Now what does this mean? This means that 25% of the observations must be less than 14. Now let's see why this is the case. So if we eliminate this, then the observations 7 and 8, in other words 2 out of the 8 and 2 out of 8 is a quarter, or 25% of the observations lies below 14, while 6 out of the 8, or 3/4, which is 75%, will lie above. So therefore, in general, 25% of the observations will always lie below the lower quartile, while 75% will lie above the lower quartile. Then we get to the rank of percentile 50. So that's clearly 50 times 8 over 100. 50 goes in 100 twice, so that's 4 plus 1, 5. So the rank of percentile 50 is 5, and therefore percentile 50 is 19. Percentile 50 is also known as Q2, or more commonly known as the median, as we had before, indicated by ME. Now this implies that if we focus on the value of 19, then it's pretty clear that 4 values out of the remaining 8, in other words half, or 50% of them lies below, while 50% lies above this particular value. The fourth one is the rank of percentile 75. Again, if we use the formula, it's 75 times 8 over 100. If you simplify this, you get 7. So therefore, the rank of percentile 75 is 7, and therefore percentile 75 is 30. Now, percentile 75 is also an important percentile. It's indicated by Q3, known as the upper quartile. So what does that mean? Percentile 75 we focus on 30, it means that 6 of the 8 remaining values, or 3/4, or 75%, lies below, while 25% lies above the upper quartile. And finally, the rank of percentile 100. If you work this out, it's pretty clear to see that it's 9. So percentile 100 is ranked at 9. So therefore 45 is percentile 100. You can say it's Q4, but this really is the maximum value. The important values that we are interested in is these 5 values: the minimum value, the lower quartile, the median, the upper quartile, and the maximum value. Now here what you can see is that 8 out of the 8, in other words 100% of the values, lie below or are less than percentile 100. Let us focus on first, second and third quartiles. Now quartiles are the 3 data values that divide an ordered set into 4 groups, where each group contains an equal number of data values. So if you have your data set and you have Q1, Q2 and Q3, remember Q1 is percentile 25, Q2 is percentile 50 or the median, Q3 is percentile 75 or the upper quartile. If we focus on Q1, it means that 25% of the data lies below. 25% of the data lies between Q1 and Q2. Another 25% lies between Q2 and Q3, and a 25% above Q3. So therefore we have the 4 groups, each containing 25% of the data. Now, as we've mentioned before, Q1 is percentile 25 and it's known as the lower or first quartile. And this simply means that 25% of the values in the data set are less than Q1. Or another way of saying it is that to say that 75% of the data set are greater than Q1. While for Q2 or percentile 50, it is really the median. This means that 50%, you can see 25 plus 25, 50% of the values in the data sets are less than Q2 or the median, while 50% of the values in the data sets are greater than Q2, the median. And finally, if we focus on Q3 or percentile 75, the upper or the third quartile, upper quartile or the third quartile, then 25 plus 25 plus 25, in other words 75% of the values in the data set will be less than Q3, while 25% of the values will be greater than Q3. Let us look at the meaning of interquartile range and semi-interquartile range. Now the interquartile range, indicated by IQR, is a measure of dispersion and is calculated by subtracting Q1 from Q3. So the interquartile range is Q3 minus Q1. So if I again look at the 3 important quartiles, which divides the data set into 4 equal portions, then the interquartile range is really that particular area, stretching from Q1 to Q3. So the range just indicate the width of it, but it gives us an idea of the spread of the middle 50% of the data set. While the semi-interquartile range is defined as half of the interquartile range. So half of that. So if we draw a line here, then this could be an indication of the spread of 25% of the data values between Q1 and the median, or 25% of the data values between the median and Q3. We now look at the 5-number summary and a box and whisker plot. Now a box and whisker plot is a graph representing the sample distribution by a rectangular box covering the interquartile range, and the whiskers at the end of the box indicating the central dispersion beyond the quartile range. Now the 5-number summary is the 5 numbers that we've seen before or discussed before. Remember, the minimum was actually percentile 0, Q1 was percentile 25, median was percentile 50, Q3 was percentile 75, and the maximum percentile 100. Now these 5 numbers in this order is known as the 5-number summary, and we need the values of these 5 before we can draw a box plot or box and whisker plot. So all it really means is we draw a box like this. Now the left edge of the box is the value of Q1, while the right edge is Q3, and we know by now that the interquartile range is that spread between Q1 and Q3. We also need to indicate the median or Q2, as well as the lowest class limit or the minimum, and the largest class limit or the maximum. And these 2 lines that we draw here from Q1 to the minimum value and from Q3 to the maximum are known as the whiskers. So this gives us a clear indication of the spread of the data. We are also interested in the location of percentile classes for group data. Only the location, not the calculation. Let's revisit our example where we have the test marks obtained by 35 students for a mathematics test counting out of 50. So what I've indicated here is the upper limits. Now remember, when you calculate the range for data and its group data, then the range is the lower limit of the first class, the difference between the lower limit of the first class and the upper limit of the last class. So the range here is 50 minus 0, or simply 50. So I've indicated all the upper limits here, as well as the frequencies, right? That adds up to 35. And then we include here what we call the cumulative frequency, as I've discussed earlier, and we get this simply by constant addition of the frequency of a class to the sum of the previous frequencies. So that should not be too difficult. But then it's much better to express this as a percentage of the sample size. So if I take 2 and divide it by 35 and express that as a percentage, I get 5.71. I do the same for 8, same for 22, 30, and 35. Now, what does this relative cumulative frequency then mean? If I can just look at 2 interpretations. For instance, if we focus at 22.86%, then we say that 22.86 of the learners scored a mark smaller or equal than 20. So we focus on the upper limit. Well, if we look at class 4, That means class 4 with an upper limit of 40, that 85.71% of the learners scored a mark of smaller or equal to 40. Now this can be easily used to identify the location of the percentile classes. Where, for instance, is percentile 25? Percentile 25, this one only goes up to 22.86%, so percentile 25 must be located somewhere in class 3. Percentile 50 is also located in exactly the same class, while percentile 75 must be more than 70, or at least equal to 75%, so it must be located right in class 4, while percentile 90 clearly will be located in class number 5. This is all we need to focus on in grade 10. The calculations of these percentiles will be discussed in grade 11 in the CAPS curriculum. In tutorial 5, the focus is on measures of dispersion for ungrouped data. Now, a long-distance runner recorded his last 15 practice runs, and the distances in kilometer are given here. It's expected of you to determine the 5-number summary for the data above, in other words, calculating percentiles 0, 25, 50, 75 and 100, and then draw a box and whisker diagram for the data. I suggest that you pause the video, do tutorial 5, and then come back and view possible solutions. Let us look at the suggested solution to problem 1 of tutorial 5, where we need to find the 5-number summary. So we arrange the data in increasing order, as here, and we determine the median. Now the median, of course, is the middle value. We can, of course, work out the rank. Remember, the median is Q2 or percentile 50. And here I've used another formula. We say that the rank of percentile 50 is the percentile, the sample size, which is 15 plus 1, which is 16. Obviously, 50 goes into 100 twice, so we get the rank is 8. So, therefore, the median is in position number 8, or is equal to 21. Note, that will mean that if we count here, we say 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7. So 7 of the remaining 14 data values are below, and 7 of the 14 above. So 50% are below and 50% above. What about the 17? That is the lower quartile, or percentile 25. Again, if I use the same formula, I find that the rank is 4. So that is 4. So in other words, 3 of the data values are below and the rest above. So that will be 25% of the data values will be below. While 26 is the upper quartile, and I've worked out the rank. I challenge you to use that alternative rank formula to recalculate this. There may be slight differences, but it really is not that important. So here I've calculated the rank, and I find that it's 12, so therefore that is the upper quartile. Clearly the minimum value is 10, and the maximum value 32. Remember, the minimum value is percentile 0 and the maximum is percentile 32. And there we have now our 5-number summary, which is important information that we will need before we can sketch the box and whisker plot. Let us consider a suggested solution to problem 2 of tutorial 5. Now here is the athlete's data, and I've indicated percentiles 0, 25, 50, 75 and 100. Note that the quartiles Q1, Q2 and Q3 divide the data set into 4 equal parts. There's 3 there, there's 3 data values between here, there's 3 between there and 3 at that end. So each one containing 3. Now, this was the 5-number summary. How do we go about to sketch the box and whisker plot? Well, you've got to start off by drawing a number line and then draw the box. Now the left edge of the box must be at 17. The right edge of the box must be at the upper quartile at 26. So then we can complete the box. The height of this box can be anything. By the way, you can also draw, this is a horizontal box and whisker plot. You can also draw it in a vertical way. It's also important that we indicate the median, namely at 21. Then we mark the minimum and the maximum, and we connect the lower quartile with the minimum and the upper quartile with the maximum to obtain the whiskers. We can relate a box plot to symmetric distribution. Now, if we consider the histogram and the box plot here, we find the data is equally spread around the median. The box plot is also symmetric. That means the median is in the middle between Q1 and Q2, and the whiskers are approximately equal in length. So such a box plot is a clear indication of a symmetrical distribution. Let's try and relate a box plot to data which indicates a positively skewed distribution. Something like this, where we have quite a few very small values. Remember the tail developing towards the left. Imagine you can draw a frequency polygon. Right? So that's why, although I have a histogram here, if you focus on the midpoints and anchor it, you get your frequency distribution polygon. So what do we find here? There's a cluster of data values at the left hand side of the distribution. So there's a lot of smaller values. The box plot is positively skewed. You see, it's sort of dragged out to the right. The right whisker is very long. The median is off center. It's more towards the left. Look at the semi-interquartile ranges. Now between Q1 and the median there is 25% of the data values, and the same, the semi-interquartile range between the median and Q3, there's also 25%, but this is more spread out. There it's more sort of clustered. We find that the left whisker is shorter while the right whisker is longer, so the data is more spread, right, on the right than on the left. So it's more dragged out, right, to the right than to the left. Finally, we want to relate a box plot to a negatively skewed distribution. Something like this, where we have quite a few very large numbers. Now there is a cluster of data values at the right hand side of the distribution. So in other words, quite a few very large values. The box plot is negatively skewed, so it tailed off towards the left. Again, I challenge you to simply go and draw on top of this a frequency polygon. The median is off center and generally towards the right, so this have an impact on the semi-interquartile range. Can you see between Q1 and ME, the median, the 25% of the data values is sort of more spread, while the 25% between the median and Q3 is more clustered. The values between the minimum and Q1 is also spread more, while the values between Q3 and the maximum is more clustered. So therefore, an indication of that is the long left whisker and the shorter right whisker. We ask a final question: to what extent can the box plot be an indication of outliers in the distribution? Now remember, distribution with outliers is caused by values that clearly stand out from the main body of data. Long whiskers due to very large or small values, data values, are normally a very clear indication of that. An outlier might signal an error in the data, and therefore it is often best to remove these outliers before we continue with the analysis of the data. So again, if we would look at a box plot in such a case, can you see there's a relatively long right whisker and a long left whisker, and this is simply due to these outliers. So this is an error in the data, so it is best to remove the outliers before we go to a further analysis of the data. We've come to the end of the video on statistics. Remember to consult textbooks for additional examples. Attempt as many possible other similar examples on your own. You may find these in some textbooks or some other publications. You should have the Shuttleworth books in your possession by now. Another good book that I would suggest is the Answer series and also the Pythagoras series. Compare your methods with those that were discussed in the video. Repeat this procedure until you are confident. Remember, there's only one way to learn mathematics, and it's firstly to make sure you understand it. But understanding doesn't mean that you know it. You need to repeat this process until you are confident. Do not forget, practice makes perfect. Good luck and goodbye.